For years, they told us it was almost here, a machine so powerful it would rewrite medicine, crack every code, remake the world, and it was always just a few short years away. So we waited, and a strange thing happened while we were waiting. The closer we looked, the further away it drifted. The confident numbers quietly vanished from the plans. The promised uses thinned out, one by one, like lights going off in a house at the end of the night, and yet, right now, the most powerful nations on Earth are pouring fortunes into it, more than ever before, into a machine that still cannot do the one thing it was sold to do. So what exactly is happening here, in the strange gap between what we were promised and what is real, and what does it mean that we may have been wrong about all of it? Get comfortable and settle in. Subscribe if you have not already, and stay with us tonight, because the story of what quietly went wrong with the quantum dream turns out to be gentler and stranger, and far more human than the headlines ever let on. Let us get into it. Part 1. The Two Roadmaps. Somewhere in the last few years, without a single announcement, the future of quantum computing was quietly rewritten, and almost nobody noticed the moment it happened. I want to start tonight with something strange. Not strange in the way we usually mean it when we talk about the quantum world, where a single particle drifts through two openings at the same time, or where two objects on opposite sides of a room seem to share one fate. That kind of strange is old news to anyone who has spent time with this subject, and honestly, it has become almost comforting. No, the strangeness I want to sit with tonight is a different kind entirely. It is the strangeness of a whole industry that appears to be walking down two roads at once, following two maps that do not agree, and hoping that if it keeps moving confidently enough, no one will ask why the maps have stopped matching. Let me show you what I mean, gently, because this is the thread we are going to follow for the next couple of hours, and it is worth getting right from the beginning. A few years ago, one of the largest companies working on this technology published a plan. Not a vague promise, but a real dated map of the road ahead. And on that map were numbers you could hold in your hand. By the year 2025, the plan said, they would have a machine with more than 4,000 of the basic building blocks of a quantum computer, the little logical units we call qubits. By 2026, they would be climbing past 10,000, and then further still, into a range where, in theory, the real power of these machines was supposed to wake up. You could circle those dates on a calendar. You could wait for them. That was the point of publishing them. Now go and look at the current version of that same map. Go and look at where those numbers used to be. They are gone. Not revised downward, not delayed by a year with an apology, not footnoted with an explanation. They have simply, quietly disappeared. The way a name disappears from a guest list when no one wants to talk about why it was removed. In their place, you will find softer language, words like error correction and logical qubits, and a new machine promised for the end of the decade. And I want to be fair here because there is a genuine and honest reason for that change, and we are going to spend real time understanding it. But I also want you to feel, right at the start, the quiet oddness of what happened. A number you could check became a milestone years away. A countdown became a horizon. And the whole thing was done so smoothly that most of the world is still repeating the old promise without realizing the promise itself has moved. Picture it for a moment, because I think seeing it makes it real in a way that just hearing about it never does. Imagine you're standing in a long, quiet corridor, the kind you find in an airport late at night, and on the wall there are two departure boards side by side. The one on the left is the old plan. It is bright and crowded and confident, every row filled with rising numbers and near dates, thousands of qubits, then tens of thousands, each one lined up next to a year that felt close enough to touch. You can almost hear the certainty in it. Now your eyes drift to the board on the right, the newer one, and something has changed that you cannot immediately name. The rows are thinner, the hard numbers have softened into gentler words, the years have slid further out, past the ones you were watching for, and there was no voice over any speaker to tell you that your flight had been delayed. The board simply updated while you were looking somewhere else, the way a departure quietly rolls from on time to delayed, and the people around you kept walking toward their gates as if nothing at all had shifted beneath their feet. That is the feeling I want you to hold on to, not alarm. Just the small, cold vertigo of realizing that a future you were counting down toward has been moved, without ceremony, a little further away. I called this business strange rather than science strange, and I want to hold on to that distinction because it is the whole key to tonight. The science of quantum computing has not misbehaved. The particles are doing exactly what the equations say they should. What has misbehaved is something on the human side of the glass, the roadmaps and the press releases and the funding announcements, the stories we tell about the machines rather than the machines themselves. It is the story that keeps walking down two roads at once. And stories, unlike particles, can be steered by what we hope and by what we fear and by what we would rather not admit, which is exactly why they are worth watching this closely. The promise seeped into everything, quietly, the way water finds every crack. It shaped where clever young people chose to spend their careers, because who would not want to be present at the birth of a new kind of machine? It shaped where money flowed, billions of it, from investors who did not want to be the ones who missed the beginning. It shaped the headlines, which learned to reach for the word revolution whenever the subject came up. And it shaped something quieter in the rest of us, a low background certainty that somewhere out there in a laboratory we would never see, the future was being assembled, and that one day soon it would simply arrive, finished, and change everything. That certainty was pleasant to carry. It asked nothing of us, and it was built, we were about to discover, on a foundation far less solid than the confidence of the people carrying it. We were told it was almost here. That phrase is going to come back tonight, again and again, so let me plant it now, cleanly, the way it was first planted in all of us. We were told the quantum computer was almost here. Almost. Right around the corner, a few short years away. And for a long time, most of us simply believed it, because the people saying it were serious, and the science underneath it was real, and the word almost is a very comfortable word to live inside. It asks nothing of you except patience. But the more carefully you look at what has actually happened over the past few years, the more you start to suspect something that is difficult to say out loud, and that is the quiet worry at the center of this whole story. Maybe we were wrong. Not foolish, not fooled exactly, but wrong in some ordinary, honest way about what we were watching, and about how close it really was. That phrase is going to come back too. We were wrong. Hold it lightly for now. By the end of tonight I want to have earned it, and I want to show you that being wrong, in the way we were wrong about this, is not an embarrassment at all. It is one of the most human things there is, and it may even be the most honest part of the entire story. But we're getting ahead of ourselves, and the whole spirit of this channel is that we do not rush. So let us slow all the way down and start where every honest version of this story has to start, with a simple question that almost nobody stops to ask, even now, even after all the billions and all the headlines. What actually is a quantum computer? Because if we are going to understand why the map keeps changing, we first have to understand the machine the map is supposed to be leading us to, and the machine is far stranger and far more limited than the promise ever let on. Part 2. What the machine actually is. A quantum computer is not a faster version of the machine you are listening to me on right now, and that single misunderstanding is the source of almost everything that has gone wrong with how we talk about this technology. Let me build it up slowly, the way you would build up a fire on a cold night, one small piece at a time. The computer in your pocket, the one in your lap, the enormous ones humming in warehouses that serve you everything you watch and read, all of them think in the same simple language underneath. They think in bits. A bit is the smallest possible decision a machine can make, a single fork in the road, and it can point one of only two ways. We usually call those two ways 0 and 1. Every photograph, every song, every message you have ever sent, every number ever crunched by any ordinary computer in the history of the world, all of it, at the very bottom, is nothing but an immense procession of these tiny two-way switches, each one settled firmly into 0 or into 1. That is the entire alphabet. 2 letters. Everything else is arrangement. A quantum computer replaces that little switch with something that behaves according to the rules of the quantum world, and those rules are genuinely, honestly strange, in the good and proper sense of the word. We call the new switch a qubit, which is just a short way of saying quantum bit. And here is the first surprise. A qubit does not have to settle into 0 or into 1 while the computer is thinking. It can hold itself in a kind of balanced, blended condition that is partly 0 and partly 1 at the same time, a condition physicists call superposition. It is not that the qubit is secretly one or the other, and we simply do not know which. It is that, until the moment we look, the qubit genuinely has not decided, and the mathematics that describes the world insists on treating that undecided in-between state as something real, something you can compute with. The usual way people try to picture this is a spinning coin, and the picture is worth using as long as we are honest about where it breaks. While a coin is spinning on a table, it is neither definitely heads nor definitely tails. It is a blur, a whirl of both, and only when you slap your hand down on it does it settle into one face. A qubit in superposition is a little like that spinning coin, a blur of 0 and 1 that only settles when you look. But here is where the picture fails, and the failure is important. A spinning coin is really only ever heads or tails at each instant, moving too fast for your eye to catch. The qubit is not like that. It is not secretly 0 or 1 while pretending to be both. The in-between condition is the real condition, as real as the settled one, and it is described by numbers that can be added and subtracted and combined, numbers the machine can actually work with while the coin is still, so to speak, in the air. That is the part with no everyday counterpart. You cannot do arithmetic with the blur of a spinning coin. You can do arithmetic with the blur of a qubit, and that arithmetic is the whole game. And now let me put entanglement back on top of that, because entanglement is where the blur becomes genuinely powerful rather than merely strange. Take two of these spinning coin qubits and entangle them, and you no longer have two separate blurs. You have a single, shared blur that describes both of them together, a combined pattern in which certain possibilities are woven tightly to certain others. It becomes possible to arrange things so that the two coins, whenever they finally settle, must settle in a related way, one matching or opposing the other, even though neither had decided until the instant of looking. Now stack not two, but dozens, hundreds, thousands of qubits into one shared, entangled blur, and you have a single object holding a weighted pattern across an unimaginable number of possibilities at once, every possibility carrying its own strength, its own emphasis, the whole thing trembling like one immense chord waiting to be resolved. That object, that shared and trembling chord, is what a quantum computer computes with. Nothing in the ordinary world of settled bits can hold it, or hum it, or resolve it into an answer. And that, and not the mere counting of possibilities, is the true and narrow miracle at the centre of all of this. I said narrow, and I want you to hold on to that word as tightly as you hold on to the word miracle, because tonight lives in the tension between the two. It is a miracle, this trembling chord of a woven possibility, genuinely one of the strangest and most beautiful things human beings have ever learned to make. And it is narrow, terribly narrow, useful only for the rare problem whose shape happens to fit it. Both of those are true at the same time, and almost every confusion about quantum computing comes from someone letting go of one of them. Let go of the miracle, and you become a scoffer who thinks the whole thing is a fraud, which it is not. Let go of the narrowness, and you become a believer who thinks the machine will soon do everything, which it will not. The honest place to stand, the only honest place, is right in the middle, holding both words at once, a miracle that is narrow, a wonder with a very particular and very small keyhole. If you can hold both of those in your mind at the same time, without letting either one go, then you already understand this subject better than most of the headlines that have ever been written about it. And it is worth resting in that middle place for a moment, in the quiet of it, before we go on. Because there is a temptation, whenever a subject turns out to be more limited than we were promised, to feel cheated, to swing hard into disappointment, and that swing is its own kind of mistake. The chord is still real. The cold machines humming in their laboratories tonight are still doing something no ordinary machine has ever done, holding a woven pattern of possibility steady against the pull of the whole warm world. That it only helps with a few problems does not make it less wondrous that it works at all. A key that opens only one lock is still a key, and if the lock it opens is strange enough and important enough, the key is worth a great deal of care. So keep the wonder. We are going to spend the rest of tonight watching the promises around this machine come apart, and I do not want you to mistake the coming apart of the promises for the coming apart of the science. The science holds. It is only the story that frays. Now this is the exact point where the popular story tends to leap ahead and get everything slightly wrong, and I want to slow down and get it right, because the mistake here is the seed of all the disappointment that follows. The popular story goes like this. If one qubit can be 0 and 1 at once, then 2 qubits can hold 4 possibilities at once, and 3 qubits can hold 8, and every time you add a single qubit you double the number of combinations. 2 qubits give you 4, 3 give you 8, 4 give you 16. By the time you reach 300 qubits, the number of combinations is larger than the number of atoms in the observable universe. It grows explosively, unstoppably, the way a rumour grows. And so, the story concludes, a quantum computer is powerful because it can somehow be in all of those combinations at once and do all of the calculations in parallel, and that is where its magic comes from. It is a beautiful story. And the part about the numbers exploding is completely true. For a collection of qubits, the number of possible arrangements really does grow as 2 multiplied by itself once for every qubit you add, what mathematicians write as 2 to the power of the number of qubits. That growth is real, and it is staggering. But here is the quiet, inconvenient fact that almost never makes it into the headline. That explosive growth all by itself is not where the power comes from, and the reason is simple, once someone finally says it plainly. An ordinary computer, the boring classical kind, also has 2 to the power of the number of bits possible arrangements. A string of 300 ordinary bits can also be arranged in more ways than there are atoms in the universe. The number of possible configurations is exactly the same. The only difference, the story says, is that the classical machine can only be in one of those arrangements at a time, and that is true. But being able to list an enormous number of possibilities is not the same as being able to use them, and the mere size of the list was never the secret. If it were, your laptop would already be a god, because your laptop can represent unthinkably large numbers of arrangements too. So where does the real power come from? It comes from 2 ideas working together, and I want to name them both carefully, because these 2 ideas are the genuine treasure at the centre of this whole field, the part that is real and beautiful and worth every ounce of the wonder we have poured into it. The first idea is entanglement. When qubits become entangled, they stop being separate little switches that each carry their own answer. They fuse, in a sense, into a single shared object, so that the state of one is bound up with the state of another in a way that cannot be pulled apart or described piece by piece. You cannot say this qubit is doing this while that qubit is doing that. There is only the whole, only the pattern they make together, and this lets a quantum computer hold something an ordinary computer simply cannot hold. It can hold a carefully weighted combination of many possibilities at once, where each possibility carries its own strength, its own emphasis, tuned by the machine. Imagine not just a list of every possible answer, but a single sound made of all of them, where some notes are loud and some are faint and the whole thing rings as one chord. That chord has no counterpart in the world of ordinary bits. It is a genuinely new kind of thing to compute with. The second idea is interference, and this is the part that turns the chord into an answer. Because these weighted possibilities are wave-like, they can be made to overlap and combine, the way ripples do when 2 stones are dropped into still water. Where the ripples rise together, they reinforce and grow taller. Where one rises as the other falls, they cancel and flatten into stillness. A quantum algorithm is, at its centre, a piece of choreography. It is an arrangement of steps designed so that all the wrong answers, the paths you do not want, line up in exactly the way that makes them cancel each other out and vanish, while the right answer, the path you're hunting for, is left standing, reinforced, loud, the one ripple that survives when all the others have flattened into calm. That is the trick. Not doing every calculation at once in some brute force parallel army, but sculpting a wave so that the noise erases itself and only the signal remains. I find that genuinely wonderful, and I want to sit in it for a moment before we go on, because the rest of tonight is going to be, in some ways, a story of disappointment, and I do not want you to mistake the disappointment for cynicism. The science here is not fake. The strangeness is not a trick. A machine that computes by tuning and cancelling waves of possibility is one of the most remarkable ideas the human mind has ever had, and the people who built the first working versions of it did something historic. When you hear me question the promises later, hold on to this part. The chord is real. The cancellation is real. What we were wrong about was never whether this beautiful thing exists. It was something else, something quieter, and we are circling closer to it. Because here is the thing about that beautiful trick. It only helps you with certain very specific problems, the ones whose shape happens to match the kind of wave sculpting a quantum computer can do. And it only helps at all once you have an enormous number of these fragile qubits working together in near-perfect harmony, and that second condition, the sheer scale required, is the first crack in the story we were told. It is where the almost begins to stretch. So let us walk right up to that crack and look into it, because it is wider than almost anyone admits. Part 3. Where the power hides. The quantum advantage is real, but it is not general, and that single distinction is the fork in the road where the public dream and the private reality quietly went their separate ways. Here is what I mean by general. When most people imagine a quantum computer arriving, they imagine a kind of universal superbrain, a machine that will simply be better at everything, the way each new phone is a little better than the last at more or less all the things a phone does. Faster at your spreadsheets, faster at your video, faster at every problem you could hand it. That is the intuition we carry from a lifetime of ordinary computers getting steadily better across the board. And it is exactly the wrong intuition for this machine. A quantum computer is not a better everything machine. It is more like a strange and specialized instrument, spectacular for a small handful of tasks whose inner shape fits its particular kind of magic, and completely unremarkable, sometimes even worse than your laptop, for the enormous majority of everything else. Think of it less like a faster engine and more like a key cut for a very unusual lock. If you happen to be standing in front of that one lock, the key is miraculous. It opens what nothing else can open. But you cannot use it to hammer a nail, or to tighten a screw, or to open any of the 1,000 ordinary doors you pass every day. It was shaped for one strange keyhole, and the tasks that fit the quantum keyhole are few and specific, and mostly not the tasks you would ever care about in an ordinary afternoon. There is a certain kind of problem in the mathematics of whole numbers, which we will come back to, and a certain kind of problem in simulating the behavior of nature's own quantum pieces, molecules and materials at their finest scale, where these machines could genuinely, in principle, leave every ordinary computer behind. But step outside that small circle of well-matched problems, and the miracle simply stops. The key finds no lock. That is the first thing the popular story left out. The advantage is narrow. But there is a second condition, and it is even more demanding, and it is the one that has quietly broken more promises than anything else. The advantage does not switch on until you have a truly immense number of qubits, all working together, all holding their fragile states in near-perfect coordination. And when I say immense, I want to give you a real sense of the gap, because the gap is the whole story. The rough estimate you will hear from serious people is that to do something genuinely useful, something no ordinary computer could touch, you would need somewhere in the range of 100,000 to 1,000,000 of these qubits, all error-free, all entangled, all singing in tune. Now hold that number, 100,000 to 1,000,000, and set it next to where the technology actually is. The machines that exist today, the real ones, the ones in the laboratories and the press releases, count their qubits in the hundreds, or at the very most a little past 1,000. And those qubits are not error-free. They are noisy, delicate, forgetful things that lose their quantum state at the faintest disturbance, as we will see. So the honest picture is not a machine that is almost there, needing one more push. The honest picture is a machine on one side of an enormous canyon, and the useful machine standing on the far side, and between them a distance measured not in a doubling or two, but in factors of hundreds or thousands, across the hardest engineering problem anyone in the field has ever faced. The word almost was doing a tremendous amount of quiet work to make that canyon feel like a step. Let me make the fragility concrete, because it is the reason the canyon is a canyon and not a hill. A qubit does not hold its blurred computing state for very long. Depending on the type of machine, it might hold it for a tiny fraction of a second, sometimes far less, before the surrounding world reaches in and knocks it into an ordinary settled 0 or 1. The tiniest disturbances are enough. A whisper of stray heat, a faint magnetic tremor from a wire in the next room, a vibration too small for any human sense to register. Any of these can reach into the machine and collapse the fragile cord before the calculation is done. So the engineers are not only trying to build more qubits, they are trying to build qubits that hold their state longer, and to run their calculations faster, and to protect the whole trembling structure from a universe that is, at every instant, trying to warm it back into ordinariness. It is a little like trying to write a long and intricate sentence in the sand at the edge of the sea, with the tide always coming in, and every new word you add gives the water more to erase. And this is why simply adding more qubits does not, on its own, carry you across the canyon. Each new qubit you add is not only more computing power, it is also one more fragile thing that can fail, one more word for the tide to reach. Without a way to catch and fix those failures as they happen, the errors accumulate faster than the power does, and a big enough calculation drowns in its own mistakes long before it can finish. So the challenge is not the flat one of piling up qubits like bricks, it is the far steeper one of piling them up while somehow keeping the whole growing pile from collapsing under the weight of its own errors. That is the true face of the canyon, and it is why the narrow, specialized nature of the machine matters so much, because you would only ever go to all this trouble, build all this fragile cold machinery and fight the tide this hard for a problem where the quantum trick genuinely wins. For anything else, for the ordinary problems of an ordinary day, it would be plain foolishness to try. Your plain, warm, sturdy laptop would win without the slightest struggle. It is worth pausing on that image of the two machines, the warm one and the cold one, because it captures something true that the marketing never wanted you to notice. The computer you are listening on right now is a warm, sturdy, general thing, happy to do 1,000 different jobs, none of them perfectly, all of them well enough, asking nothing of the world except a little electricity and a place to sit. It is a workhorse, patient and unfussy, and it has quietly become the most useful kind of machine ever built, precisely because it is so willing to do almost anything. The quantum computer is its opposite in nearly every way. It is a delicate, frozen, specialized thing, capable of one narrow kind of astonishment and almost nothing else, demanding a cathedral of cold and a fortress of shielding just to hold its thoughts together for a fraction of a second. It is not a better workhorse. It is not a workhorse at all. It is something closer to a rare and temperamental instrument, kept in a sealed and frozen room, brought out for the one kind of music only it can play. And when you hold those two machines side by side, the warm generalist and the cold specialist, you can feel how strange it always was to imagine that the second would simply replace the first, the way each new phone replaces the last. They are not competitors on the same road. They are different kinds of thing entirely, built for different kinds of task, and the dream that the cold one would soon do everything the warm one does, only faster, was a confusion from the very beginning. That confusion, quiet and rarely examined, is a good part of how the promise grew so far beyond the machine. And this is where I want to be careful and fair, because it would be easy to tip into mockery here, and mockery is cheap, and it is not what this channel is for. The people working on this are not lying. The canyon is not a scandal. It is simply the true shape of the problem, and the true shape of the problem was always going to be hard, because you are trying to build a machine out of the most fragile states that exist in nature, and hold them steady long enough to compute with them. That is genuinely one of the hardest things anyone has ever attempted. The scandal, if there is one at all, is not in the difficulty. It is in how the difficulty was described. It is in the steady stream of near dates and round-the-corner promises that turned a canyon into a countdown and left millions of ordinary people, and more than a few governments, believing that the far side was almost within reach. Because once you see the canyon clearly, a great many things that seemed puzzling suddenly make sense. You understand why the noisy little machines we have built, impressive as they are, keep failing to do anything genuinely useful. They are on the wrong side of the canyon, and no amount of clever marketing can carry them across it. You understand why the promised applications keep slipping, one after another, further into the future, and you begin to understand too why the maps had to change, why those confident qubit numbers had to quietly vanish from the roadmap and be replaced with softer, longer horizon words. Because at some point the people drawing the maps looked honestly at the canyon and realized that the old numbers, the ones you could circle on a calendar, were promising something the machine could not deliver on that schedule, and so the numbers went away. But that raises the obvious question, the one we've been circling since the very first minute of tonight. If the honest answer was always this canyon, this immense and difficult distance, then why did the maps ever show those confident near numbers in the first place? What changed between the old roadmap and the new one? What did the map makers see that made them quietly erase the very milestones they had once been so proud to publish? To answer that, we have to go back to that vanishing roadmap and look, carefully and without cynicism, at exactly what disappeared, and at the genuinely good scientific reason that stands behind the disappearance, and at the quieter, stranger thing that the good reason helped to hide. And when we do, the word almost is going to start to come apart in our hands. Part 4. The numbers that disappeared. The roadmap did not lie to us exactly, and that is what makes what happened to it so quietly unsettling, because a lie you can catch, but an honest correction that hides a retreat is a much harder thing to see. Let me take you back to that vanishing plan and show you precisely what went missing, and then show you the genuinely good reason it went missing, because both halves of this are true at once, and holding both at once is the only honest way through. The old roadmap, the confident one, spoke in a language of raw hardware. It counted qubits the way you might count bricks, as if the number of bricks told you how close the house was to being finished. More than 4,000 qubits by 2025, 10,000 and beyond by 2026, and onward from there into the range where the real power was supposed to wake up. These were the bricks, laid out year by year, and every year the pile was supposed to grow. The trouble is that a qubit is not a brick. A brick, once it is fired and stacked, stays a brick. It does not forget that it is a brick. It does not, at the faintest breath of warmth or the softest tremor from the next room, quietly stop being a brick and dissolve back into mud. But a qubit does exactly that. The fragile, in-between, superposed state that gives a qubit its power is also almost unbearably delicate. The slightest disturbance from the outside world, a stray flicker of heat, a wandering magnetic whisper, a vibration too small to feel, reaches in and collapses the balanced state, forces the qubit to fall into a plane 0 or a plane 1, and the quantum information it was carrying is simply gone. Physicists call this decoherence, which is a gentle word for a brutal fact. The very thing you're trying to compute with is trying, at every instant, to leak away into the surrounding world. Left alone, a qubit holds its magic for a flicker of time, and then it is just an ordinary switch again. This is why simply counting raw qubits was always a little bit of a magician's misdirection. 4,000 noisy, forgetful qubits are not 4,000 useful ones, because their errors pile up faster than their power accumulates, and the whole calculation drowns in mistakes long before it finishes. What you actually need is not raw qubits, but reliable ones, and the only known way to build a reliable qubit is one of the most beautiful and expensive ideas in the field, and it is called quantum error correction. The idea is this. You take many of the fragile physical qubits, the real ones on the chip, and you weave them together so that they act as a single, sturdier, protected qubit, one that can catch and fix its own errors as it goes. This protected qubit, built from many physical ones, is called a logical qubit, and the ratio is humbling. Depending on the method, it can take hundreds, or in older schemes even 1,000, of the noisy physical qubits to build up just one trustworthy logical one. Now you can see, suddenly and clearly, why the numbers on the roadmap had to change. Counting physical qubits was measuring the bricks. What actually matters is how many finished weatherproof rooms you can build, and each room costs an enormous number of bricks. So the newer roadmap speaks a different language. It has stopped bragging about raw qubit counts and started talking about logical qubits, the protected ones, the ones that can actually hold a calculation together. The same company now points to a machine promised for around the end of the decade, near the year 2029, a machine meant to be genuinely fault-tolerant, able to run about 100 million quantum operations across roughly 200 logical qubits, and to do it, if the newest error-correcting codes work as hoped, on the order of 20,000 physical qubits rather than the millions older methods would have demanded. They have even developed clever new codes that are said to cut the number of physical qubits needed for protection by around 90%, which is a real and impressive advance. This is honest science. This is the field growing up and admitting that reliability, not raw quantity, is the true measure. I want to dwell for a moment on just how steep that price of reliability is, because it reframes every qubit number you will ever hear. Picture the arithmetic. If it takes, say, 1,000 fragile physical qubits to build a single protected logical one, then a machine with 200 logical qubits, the target for the end of the decade, might need on the order of hundreds of thousands of physical qubits underneath, unless the clever new codes succeed in bringing that overhead down dramatically, which is exactly what the newest designs are trying to do. So when you hear a company announce a machine with 1,000 physical qubits today, and you remember that a genuinely useful calculation might need hundreds of protected logical qubits, each one built from a great many physical ones, you can suddenly see the true size of the gap. It is not that we have 1,000 and need a few thousand more. It is that we have 1,000 raw, noisy qubits, and need, in effect, a machine 1 or 2 entire orders of magnitude larger, and cleaner, and more coordinated than anything that exists. The raw number was always going to be a misleading measure. The logical number, the number of qubits reliable enough to actually trust, is the one that matters, and by that honest measure, today's machines have not 1,000, not 100, but a mere handful, if that. None of which, I want to insist again, is a scandal in itself. Every step of this reckoning is honest science correcting an earlier oversimplification. The move from counting physical qubits to counting logical ones is a move toward truth, not away from it. But truth has a cost when you have spent years advertising the simpler, prettier number, and the cost is that the finish line, once quietly redrawn in honest ink, is suddenly and visibly much further away than the old marketing implied. And the people who drew it further away did not, for the most part, turn around and say so plainly. They simply started using the new number and let the old one fade and hoped that no one would hold the two side by side and feel the distance between them. And yet, I want you to feel what actually happened in that honest correction, because underneath the good science there is a quieter movement, and it is the movement this whole video is about. A number you could check on a calendar was replaced by a milestone at the far edge of the decade. A promise for next year became a promise for the end of the decade. The bricks you were counting were quietly swept away, and in their place you were handed a picture of a finished house, beautiful and detailed, standing several years down a road you cannot yet see the end of. Nobody did anything wrong. Every individual step was reasonable, but stand back from all the reasonable steps, and what you see is a goal that moved further away at the exact moment you reached out to touch it. I want to stop here and slow down and let this land, because it is the emotional centre of the first half of tonight, and it deserves more than a passing mention. There is a particular ache that comes from realizing that a future you were promised has been quietly rescheduled. It is a small grief, and most of us have felt it in one form or another. You were told it was almost here. You believed it. Maybe you built something on that belief. Maybe you were a student who chose a field because the revolution was coming and you wanted to be part of it. Maybe you were an investor, or a founder, or simply a curious person who kept one eye on the horizon, waiting for the morning when the news would finally break that the machine had arrived and the world had changed overnight. And the morning kept not coming. And each time you looked, the horizon had slid a little further out, so smoothly that you could never quite point to the moment it moved. There was no announcement. There was never any announcement. The board just updated while you were looking somewhere else, and everyone around you kept walking toward their gates, and the delay was absorbed so gracefully into the ordinary passage of time that it began to feel almost impolite to ask when, exactly, almost had been supposed to arrive. That quiet, unceremonious rescheduling of a future you had already made room for in your imagination, that is the real cost of the word almost, and it is a cost paid not in dollars, but in something closer to hope. So the numbers disappeared for an honest reason, and the disappearance still hid a retreat. Both true. And once a field has learned to move its goalposts gracefully once, for good reasons, it becomes much easier to move them again, for reasons that are a little less good. Because the vanishing of the qubit numbers was not the only goalpost that moved. It was only the first and the most visible. There were others, quieter ones, and the next one is subtler and in a way stranger, because it did not move the finish line further away. It changed what counted as crossing it. Part 5. The first promise that moved. When the far side of the canyon proved too far to reach on schedule, the story did not simply admit the distance. Instead, it did something cleverer. It began to suggest that we did not need to cross the canyon at all, at least not yet, because the noisy little machines already sitting on this side might turn out to be useful just as they were. This was the first great shift in the promise, and it had a name, a technical, almost cozy name that made it sound like a well-understood stage of a well-understood journey. The machines we can actually build today, the ones with their hundreds of noisy, forgetful qubits and no real error correction, were given a label. They were called noisy intermediate-scale quantum devices. It is a mouthful, so people shortened it, and the short version became a kind of banner that a great deal of hope was hung upon. The idea behind the banner was genuinely appealing, and I want to give it its due because it was not foolish. The idea was that even before we built the enormous error-corrected far-side machine, these smaller, imperfect near-term machines might already be powerful enough to do something valuable. Not everything, not code-breaking, but something. Some useful corner of chemistry, perhaps, or some optimization problem, or some pattern in data, where even a noisy quantum computer might reach an answer that an ordinary computer could not reach as well or as fast. It was a reasonable hope. And it did something very important for the field, something that had nothing to do with physics and everything to do with patience. It filled the waiting. It gave everyone a reason to believe that the payoff was not at the distant end of the decade, but potentially right now, or almost now, from the very machines that already existed. It kept the word almost alive, but relocated it. The revolution was no longer almost here in the sense of a future machine arriving. It was almost here in the sense that the machines on the table might, any day, cross some threshold of usefulness. It was a promise that asked you to keep watching the near-term hardware with the same eager attention you had once given the distant roadmap. And here is what happened. The useful applications did not appear. I want to be careful and precise, because this is exactly the kind of claim that deserves precision rather than sweeping dismissal. It is not that these noisy machines did nothing. They ran experiments. They demonstrated pieces of algorithms. They served as genuinely valuable scientific instruments for studying quantum systems themselves and for learning how to build the next machine. That is real, and it matters. But the specific load-bearing promise, the promise that these near-term noisy devices would deliver practical value, would solve some real-world problem better than an ordinary computer, and in a way that actually mattered to someone outside a laboratory, that promise quietly went unmet. Year after year the demonstrations came, and each was described with great excitement, and each, when you looked closely, turned out to be either a problem specially chosen to flatter the quantum machine, or a result that an ordinary computer could match once someone bothered to try. The threshold of genuine, practical, near-term usefulness was announced many times and crossed. Honestly, never. Do you see the shape of it beginning to repeat? A promise is made. The promise is warm and specific and near. Time passes. The promise does not arrive. And then, rather than a clear admission that it did not arrive, the promise is quietly replaced with a new one, positioned just a little differently, so that the failure of the old promise never has to be announced as a failure. First the raw qubit numbers, which vanished into the language of logical qubits and end-of-decade milestones. Then the near-term usefulness of noisy machines, which, when it failed to materialize, did not produce a moment of reckoning but simply faded, unmourned, as the conversation moved on to the next framing. Nobody stood up and said, "We were wrong about the noisy machines being useful." The subject just gently changed. And this is the quiet machinery that keeps the word almost alive no matter how much time goes by. Almost never fails, because almost is never given a deadline it can be caught missing. It simply migrates from the distant machine to the near machine to the next idea, always staying just ahead of the evidence. Look closely at how each of those hopeful demonstrations tended to work, because the pattern is quietly revealing. A team would take a problem, and they would show that their noisy quantum machine could handle it, and the announcement would ring out. But then, often, one of two things would emerge on closer inspection. Either the problem had been chosen, consciously or not, precisely because it flattered the quantum machine, a problem shaped to fit the one thing the machine could do, rather than a problem anyone in the outside world actually needed solved. Or else, a little later, someone would sit down with an ordinary computer and a bit of cleverness, and show that the boring old machine could do the very same task about as well, or better, at a tiny fraction of the cost. Neither outcome is fraud. Both are the ordinary friction of a young field feeling its way. But together they meant that the load-bearing promise, the promise that these near-term machines would do something genuinely, usefully, undeniably beyond the reach of ordinary computers, kept dissolving on contact with careful scrutiny. And each time it dissolved, the conversation moved on before anyone had to say the words out loud. I do not say this with anger, and I hope you do not hear anger in it. I say it with a kind of tenderness, actually, because this pattern is so very human. None of us likes to announce that we were wrong. We would all rather quietly adjust the story and keep moving, and hope that no one lines up the old version next to the new one. Whole fields do this. Whole industries do this. It is not villainy. It is the ordinary way that hope protects itself from disappointment, by never quite letting the disappointment be named. And I think there is a lesson in that pattern that reaches far beyond this one technology, which is why I keep returning to it so gently, rather than with a pointed finger. Almost every field that promises to change the world moves through some version of this rhythm. The promise is made in the bright, round language of certainty, because certainty attracts attention and money and talent. The reality turns out to be slower and narrower and more stubborn than the promise. And then, rather than a public reckoning, there is a quiet migration of the goalposts, a softening of the language, a shift of the subject, so that the gap between what was promised and what arrived is never quite laid bare. It happens with new medicines, with new energy sources, with new machines of every kind. It is not mostly the work of liars. It is the work of hopeful people protecting their hope from the cold water of a deadline. And the only real defense any of us has against it is the small, unglamorous habit of asking, whenever we're told that something is almost here, a single quiet question. Almost here by when, and how would we know if it were not? That question sounds cynical, but it is the opposite of cynicism. Cynicism says none of it is real and walks away. This question says, I take the promise seriously enough to ask it to be specific, to give me a date I could check and a result I could recognize, so that if it arrives I will know to celebrate, and if it does not, I will know not to keep waiting. That is not a hostile question. It is a respectful one. It is the question that separates genuine anticipation from the endless, comfortable, unfalsifiable waiting that the word almost invites us into. And it is the question that almost no one thought to ask about quantum computing for the better part of a decade, which is exactly how a decade of not arriving managed never to feel like a decade of not arriving. But the cost of never naming it is that the same move can be made again, and each time it becomes a little smoother, a little more practiced. And the third time it was made, it was the smoothest of all, and it produced something genuinely remarkable to look at, a demonstration so impressive that it was celebrated around the world. And yet, when you read the fine print, it quietly told on itself. It is one of the strangest documents in this whole story, and we're going to read it together now. Part 6. The Machine That Agreed with the Old One. There is a particular kind of magic trick where the magician shows you very openly that nothing is hidden, and it is precisely that openness that keeps you from noticing what actually happened. The third goalpost move was a trick like that, performed in full view, and it centered on a molecule. Here is the setup, and it is genuinely worth admiring before we look underneath it. Not long ago, one of the largest companies in this field, working together with a famous medical research institution and a major scientific laboratory, announced that they had used a quantum computer to help simulate a protein, and not a small one. A protein is a folded chain of atoms, one of the intricate molecular machines that run the chemistry of life, and simulating how one folds and behaves is a famously hard problem, the kind of problem that ordinary computers strain against because the quantum behavior of all those atoms is so tangled. The protein they modeled contained something like 12,600 atoms, tens of thousands of the orbital patterns that electrons can occupy, a molecule far larger than anything of its kind that had been approached this way before. They used up to about 94 qubits to do it. And the headline wrote itself. A quantum computer had helped simulate one of the machines of life, at a scale never reached before. It sounded at last like the future arriving. It sounded like a use, and it was real work. I want to say that clearly, because I think what these teams are doing is genuinely interesting and genuinely difficult, and I have no wish to sneer at it. But now let us do the thing almost no one does with a press release. Let us read the fine print, the part written by the scientists themselves, in their own careful language, buried where excitement rarely reaches. Two things are written there, quietly, and together they change the entire meaning of the announcement. The first thing is how the calculation was actually done. It was not done by a quantum computer. It was done mostly by an ordinary one. The approach they used has a new and important sounding name, quantum-centric supercomputing, and when you translate that name out of the language of marketing and into the language of plain description, it means something much more modest. It means hybrid. It means a partnership in which a large classical supercomputer, the ordinary kind, does the overwhelming majority of the work, and a quantum processor is brought in to handle a few of the most tangled pieces. The molecule is broken up into parts, and the ordinary computer handles most of the parts, and the quantum machine is handed a small, especially knotted corner of the problem. It is a sensible way to work. But notice what has happened to the story. We began, years ago, with the dream of a quantum computer that would do the whole calculation and leave ordinary computers behind. We have arrived at a quantum processor that helps out with a corner, while an ordinary supercomputer does the heavy lifting. The machine has gone from the star of the show to a supporting player, and the name quantum-centric was chosen, I suspect, to keep the word quantum at the centre of a sentence where the quantum part is no longer at the centre of the work. The second thing written in the fine print is even quieter and even more telling. The researchers compared the result they got from their hybrid quantum and classical approach, against the result you would get from the most demanding purely classical methods, the best ordinary techniques, no quantum machine involved at all. And they reported, in their own words, that the two results were comparable. Comparable. Sit with that word for a moment, because it is doing something extraordinary. It means that the answer produced with the help of a 94-qubit quantum processor at the frontier of one of the most expensive and celebrated technologies on Earth was about as good as the answer an ordinary computer could produce on its own. Not dramatically better. Not reaching some answer the classical machine could never touch. Comparable. Let me put you inside that result because I think you have to feel it to understand why it matters. Imagine you're standing in a quiet control room, watching two screens. On both screens, the same protein is slowly folding, thousands of atoms drifting and settling into the shape that will let this little machine of life do its work. The folding is beautiful, patient, almost like watching frost spread across a window in slow motion. On the left screen, the simulation is being run with the help of the quantum processor, the machine cooled to near absolute stillness, the qubits singing their fragile chord. On the right screen, the same protein is folding, guided only by an ordinary supercomputer, the same kind of machine that renders films and forecasts weather. You lean in close. You look for the difference. You look for the moment where the quantum-assisted protein on the left pulls ahead, reaches some shape or some accuracy the ordinary one on the right cannot match, and you cannot find it. The two proteins settle into the same shape, at about the same quality, and if someone had not labelled the screens, you could not tell which one had been touched by the quantum machine and which one had not. The drama of the scene is not a triumph. The drama is the absence of a difference. That is the strangest thing to witness. Two answers arriving side by side, and the frontier technology leaving no fingerprint you can find. This is the genuine, quiet catch at the centre of the hybrid approach, and it is almost too perfect. When a classical supercomputer does most of the work, and the final answer is about as good as a classical supercomputer would have produced anyway, then it becomes very, very hard to point to the quantum machine and say, there, that part, that is what the quantum computer brought us. The quantum contribution is folded so thoroughly into the classical work, and the result is so close to the purely classical result, that the specific value added by the quantum processor becomes almost impossible to isolate. The demonstration is impressive precisely in a way that cannot be pinned down, and I do not think that ambiguity is entirely an accident. A result you cannot quite disentangle is a result that can be celebrated without ever being cornered. I want to be scrupulously fair to the hybrid approach, because there is a version of this that is genuinely sensible and even wise, and I do not want my unease to curdle into dismissal. Using an ordinary computer for the parts it handles well, and calling in a quantum processor only for the few knots that are truly quantum in nature, is exactly the kind of pragmatic engineering you would expect from serious people making the best of the machines they actually have. If quantum processors are small and noisy today, then leaning on classical supercomputers for the heavy lifting is not a cheat. It is common sense. There is nothing wrong with the method. The unease is not about the method. The unease is about the word comparable, and about what that word quietly confesses. Because think about what it would take for one of these demonstrations to be truly convincing. To silence every doubt at once. It would need to produce an answer that the best ordinary computers simply could not produce, a result that no classical machine could match at any reasonable cost, so that you could point at it and say, there, that, only a quantum machine could have done that, and here is the proof. That is the demonstration everyone is waiting for, and that is precisely the demonstration that has not arrived. Instead, we get results that are comparable, results about as good as what the ordinary machines could already do, results where the quantum contribution is folded so thoroughly into a classical calculation that no one can cleanly say what it added. It is genuinely impressive work. It is a real step in learning how to use these machines. But it is not the thing we were promised, and the gap between an impressive step and the promised arrival is exactly the gap the word almost keeps papering over. When the fine print says comparable, it is telling you, in the most honest language the researchers have, that the quantum advantage everyone is waiting for was once again not quite there, not absent, not fraudulent, just, once again, almost. Which brings us at last to a phrase I want to plant now and return to later, because it cuts through all of this to the thing underneath. All through these years we have been told a story in which the great challenge was building the chips, fabricating the delicate quantum hardware, and that once we could manufacture enough qubits, the revolution would follow. But look at what the fine print keeps revealing. The chips are not the thing standing in the way. We can build remarkable machines. We can cool them, wire them, print their qubits, chain 90 of them together and point them at a protein. The hard part was never the chip. The hard part is finding something for the chip to do that an ordinary computer cannot already do about as well. And that, it turns out, is a far harder problem than any problem of manufacturing, because it is not a problem of engineering at all. It is a problem of whether the miracle, the narrow and beautiful miracle we spent so long admiring, actually has a place to happen in the ordinary world. And when you start asking that question honestly, and go looking for the places the miracle was supposed to happen, you find something sobering. One by one, over the years, those places have been quietly emptying out. Part 7. The Rooms That Emptied. For years, whenever anyone asked what a quantum computer would actually be good for, the same 4 answers came back, again and again, like the names of 4 grand rooms in a house that was still being built. And if you go and visit those 4 rooms today, one by one, and stand in each of them and look around honestly, you find something that is difficult to say and important to understand. Most of them are emptier than they were when the tour began. The first room was always chemistry, and it was, of all 4, the one with the strongest claim to be real. The argument was elegant. Nature, at its finest scale, is quantum. The way electrons arrange themselves inside a molecule, the way atoms bond and break and rearrange, all of it runs on the same quantum rules a quantum computer is built to speak. An ordinary computer has to translate that quantum behavior into its own clumsy language of zeros and ones, and the translation gets exponentially harder as the molecule grows. A quantum computer, in principle, could speak the molecule's own native tongue. This was never a foolish hope. It is probably the single most defensible use these machines will ever have. But watch what happened to it in practice. When the hybrid protein simulation we just walked through finally arrived, the grandest chemistry demonstration yet, the answer it produced was comparable to what an ordinary computer could already do. The room is not empty. There may genuinely be treasure in it someday. But the treasure keeps turning out to be locked behind the same canyon we have been staring across all night, the one that only a far larger, error-corrected machine can cross. For now, the chemistry room contains a great deal of promise, and very little that an ordinary laboratory could not already have obtained. The second room was materials science, and it is really the chemistry room's next-door neighbour, sharing the same wall and the same fate. The dream was that quantum computers would let us design new materials from scratch, atom by atom, the superconductor that works at room temperature, the perfect battery, the miracle catalyst, by simulating their quantum behavior before ever building them. And again, the dream is not wrong in principle, but in practice the same thing happened that happened in chemistry. The problems that are small enough for today's noisy machines are also small enough for ordinary computers, so the quantum machine has nothing to prove there. And the problems that are large enough to matter are also large enough to demand the far-side machine we do not have. The useful territory keeps falling into the canyon. The third room was optimization, which is a plain word for an enormous and lucrative family of problems. How do you route 10,000 delivery trucks so they drive the fewest total miles? How do you schedule an airline, or pack a warehouse, or balance a financial portfolio, so that some quantity is squeezed to its smallest or stretched to its largest? These problems are everywhere, and they are worth staggering amounts of money, and for a while quantum computing was sold as their conqueror. This room may be the emptiest of all, and its emptying was the most instructive to watch, because it did not empty by itself. It was emptied by the competition. Ordinary computers, running ever cleverer ordinary algorithms, kept getting better and better at exactly these problems, so that every time a quantum method was proposed, an ordinary method rose to meet it, and usually got there first, and more cheaply. There is even a wonderful, quietly devastating episode from a few years back, around the year 2018, when a young researcher, an undergraduate student, took one of the flagship quantum algorithms, one that had been celebrated as a clear example of quantum advantage for a recommendation problem, the kind of problem that decides what a shopping site suggests you buy next, and showed that an ordinary computer could do essentially the same thing, almost as fast with no quantum machine at all. The technical name for that maneuver is dequantization, and it is exactly as deflating as it sounds. It means taking a supposed quantum triumph and showing that the quantum part was never really necessary, and it kept happening. One claimed advantage after another was quietly dequantized, matched by an ordinary method that had simply not been tried hard enough before. There is something almost poetic about that word, dequantization, and it is worth letting it sink in because it captures the strange predicament of the whole field. To dequantize a result is to reach into a supposed quantum triumph and pull the quantum part back out, and to discover that the thing still works without it, that the magic was never load-bearing. And the reason it keeps happening is quietly humbling. It turns out that trying to beat a quantum computer is one of the best ways to make ordinary computers better. Every time researchers study a quantum algorithm closely enough to understand why it might win, they often learn something that lets them build an ordinary algorithm that wins instead. The quantum idea becomes a kind of map, showing the classical world a path it had not noticed, and then the classical world simply walks that path on cheaper, sturdier legs. The quantum machine ends up improving its own competition, handing its rivals the very insights they need to make it unnecessary. And then, arriving late but moving fast, came the other great technology of our moment, the one that has spent these same years not promising and almost arriving, but actually, undeniably, arriving. While quantum computing was perpetually a few years away, artificial intelligence walked in the door and sat down at the table and began, quietly, doing several of the jobs that quantum computing had reserved for itself. Predicting how proteins fold, finding patterns in enormous piles of data, helping to design molecules and materials. These were supposed to be quantum computing's harvest, and much of it has been gathered instead by ordinary machines running clever learning programs, no qubits required, no cathedral of cold, no canyon to cross. And so the fourth room emptied not into silence, but into the sound of a different technology doing the work, while the word quantum was left standing in the doorway, still promising, still almost, watching someone else carry out the furniture it had meant to use. The fourth room was finance, and honestly the fourth room is mostly the third room wearing a more expensive suit. The promises about finance, pricing complicated financial instruments, managing risk, finding advantage in markets, were built on the same optimization dreams, and they eroded the same way, undercut by the same steadily improving ordinary methods, and increasingly by something new that had arrived in the meantime and started doing many of the jobs quantum computing had been promising to do. Because while quantum computing spent a decade being almost ready, an entirely different technology grew up and quietly walked off with several of the prizes quantum computing had reserved for itself. That technology was artificial intelligence, and this is where you notice a strange verbal tell, a little linguistic habit that tells you something has gone wrong with the argument. Whenever the specific case for quantum computing grows thin, you will often find, added to it, a sprinkle of the other magic word of our moment. Quantum computing and artificial intelligence together will deliver personalized medicine. Quantum computing will supercharge artificial intelligence. When one hard promise starts to falter, it is quietly bundled with the other exciting thing on the hope that two dazzling words together will shine brightly enough that no one asks which of them is actually doing the work. And more often than not, when you look closely, it is the ordinary artificial intelligence running on ordinary machines that is doing the work, while the word quantum rides along beside it, sharing the credit for a job it did not do. So you walk out of the 4 grand rooms and you tally what you found. Chemistry, promising but locked behind the canyon. Materials the same. Optimization, steadily reclaimed by ordinary computers. Finance the same, with artificial intelligence walking off with the rest. Not one of the 4 rooms is truly furnished. Not one of them holds the everyday, world-changing, better than what we already have application that the whole enterprise was sold on. And this is the sobering thing that almost no one says plainly. It is not that quantum computers have failed. It is that the specific, practical, valuable to ordinary people jobs they were supposed to do keep turning out to be jobs an ordinary computer can already do, or will be able to do by the time the quantum machine is ready, or that some other technology has quietly claimed in the meantime. The house was built for 4 grand purposes, and 3.5 of them have quietly moved out, and yet the house still stands, and more money than ever is being poured into it, which should already feel strange to you, and we will get to exactly how strange. But before we do, I owe you honesty, because I have just walked you through 4 empty rooms, and it would be easy to conclude that there is nothing here at all, that the whole thing is hollow. That conclusion would be wrong, because there is one more room in this house. I saved it for last, and it is not empty. It is the one room whose door no serious person disputes, the one place where a large enough quantum computer really would do something no ordinary machine ever could. It is a single room. But what is inside it is powerful enough and unsettling enough that the world's most powerful governments have decided they cannot afford to let anyone else reach it first. Part 8. The one door everyone believes in. There is exactly one thing that almost every expert agrees a large enough quantum computer could truly do, something no ordinary machine could ever match, and it is not curing a disease or designing a material or routing a fleet of trucks. It is breaking secrets. And to understand why that one use is real, when so many others turned out to be mirages, you have to understand a quiet piece of mathematics that, right now, tonight, is holding the entire modern world together. Almost everything you do that must stay private depends on a kind of lock made not of metal, but of arithmetic. When you send a message to someone you love, when your bank moves your money, when a government protects a secret, when a hospital guards your records, the privacy of all of it rests on a single elegant idea. There are certain mathematical problems that are easy to do in one direction and monstrously hard to undo in the other. The favourite example, the one that guards a great deal of the internet, is multiplication. If I hand you two enormous prime numbers, each hundreds of digits long, you can multiply them together without much trouble and get a single gigantic number as the answer. That is the easy direction. But now imagine I show you only the answer, the gigantic number, and I ask you to find the two original primes that were multiplied to make it. That is the hard direction, and it is called factoring. And here is the astonishing thing. For a large enough number, factoring it back into its two original primes is so staggeringly hard that all the ordinary computers on Earth, working together for longer than the universe has existed, could not do it. The lock is not made of steel. It is made of the fact that undoing that one multiplication is, for practical purposes, impossible. That single fact, the impossibility of factoring enormous numbers, is the hidden foundation under an immense amount of the privacy and security of modern life. It is the reason you can type your card number into a website and trust that a stranger cannot read it. It is a wall, and the wall has held for decades, and the whole world quietly leans on it without ever thinking about it. You have leaned on that wall yourself countless times, almost certainly today, without ever once feeling it. Every time you have seen a small padlock appear beside an address in your browser, that padlock was standing on this exact piece of mathematics, or one of its close relatives. When your device and a distant server needed to agree on a secret key, a private code known only to the two of them, they performed a kind of mathematical handshake in full public view, exchanging numbers that anyone could see, and yet ending up with a shared secret that no eavesdropper watching the whole exchange could work out. That trick, agreeing on a secret in the open where everyone is listening, sounds impossible when you say it plainly, and it is one of the genuine marvels of modern life, and it rests entirely on the fact that undoing certain arithmetic is, for an ordinary computer, effectively impossible. The whole architecture of trust that lets money move and messages stay private is built on that one word, impossible, and impossible here has always meant impossible for ordinary machines. Shor's method is dangerous precisely because it changes the meaning of that word. It does not make the arithmetic easy for ordinary computers, which is why the wall still stands today. It makes the arithmetic easy for a large enough quantum computer, a machine that does not yet exist. So the wall is not crumbling. It is standing exactly as strong as it ever was against every machine that currently exists. But its strength was always a kind of bet, a bet that no one would ever build a machine of a fundamentally different kind. And Shor showed, decades ago, that this bet has an expiration date written into it, a date set not by the mathematics but by the slow progress of the hardest engineering problem in the field. The wall will hold until the machine that ignores it is finally built, and then, all at once, for everything still hiding behind that particular wall, it will not hold at all. Now, in the year 1994, a mathematician named Peter Shor found something that should keep a certain kind of person awake at night. He worked out a method, an algorithm, by which a sufficiently large and reliable quantum computer could factor those enormous numbers not in longer than the age of the universe, but quickly, efficiently, in a manageable stretch of time. He found a way to use exactly that beautiful trick we talked about earlier, the sculpting of waves of possibility so that the wrong answers cancel and the right one rings out, and he aimed it precisely at the problem of factoring. And it works. There is no serious doubt that it works. If you had a large enough, reliable enough quantum computer, Shor's method would let it walk straight through the mathematical wall that currently protects the world's secrets, as if the wall were made of paper. It is worth understanding, at least in feeling if not in every detail, why Shor's method can walk through a wall that stops every ordinary machine, because the reason is a small marvel in itself. An ordinary computer, faced with an enormous number to factor, has essentially no better option than to search, to try possibility after possibility, and for a number hundreds of digits long, there are so many possibilities that the search would outlast the universe. Shor's insight was to stop searching directly for the factors, and instead to hunt for something else hiding inside the number, a kind of buried rhythm, a repeating pattern in the way certain calculations cycle around when you work with that number. It turns out that if you can find the length of that hidden rhythm, the factors fall out almost for free by a short piece of ordinary arithmetic. And finding a hidden rhythm, a repeating period buried in a wave of possibilities, is exactly the kind of task the quantum trick is built for. The machine prepares its trembling chord across a huge range of possibilities, and then arranges the interference so that everything cancels except the pattern that shares the hidden rhythm, which rings out clearly and reveals the period. The wall is not smashed, it is sidestepped, by a machine that refuses to search where an ordinary computer must, and instead listens for a rhythm that an ordinary computer cannot hear. That is why this one use is genuinely, unarguably real, when so many of the others turned out to be mirages. It is not a vague hope that a faster machine might do a familiar job a little better. It is a specific, proven mathematical method aimed at a specific, enormously valuable target, using exactly the one thing quantum machines can truly do that ordinary machines cannot. The catch, the enormous catch we are about to sit with, is that word again, the one that has haunted every promise tonight. The method is real, the target is real, the danger is real. But the machine that could actually run it, at the scale the real world requires, is not here, and is not almost here in any honest sense, and that gap between a real method and a real machine is where the whole strange story turns one more time. I want you to feel what that actually means, because it is the most literal possible version of the phrase in tonight's title, the phrase it changes everything. Let me take you into it, quietly, the way we take ourselves into these moments. Imagine for a moment that somewhere a machine like that finally switches on. Not today, and as we'll see, not for a long time, but imagine the moment anyway. All around the world, in a silence you would never hear, the locks begin to open. Not with any sound, not with any drama. Somewhere, the encrypted message a stranger sent last year, thinking it was sealed forever, quietly becomes readable. The sealed financial record, the private letter, the guarded government cable, the medical file, the years of conversations that everyone believed were locked away behind the unbreakable wall of arithmetic, one after another, without a single alarm going off, they simply click open, like a long corridor of doors all unlatching at once in the dark. Every secret that was ever protected by that particular wall, every secret anyone thought was safe, lying suddenly open to whoever holds the machine. There is no explosion, no siren. That is the strangest part. The most consequential break-in imaginable would announce itself with nothing at all, just a quiet, universal unlocking, felt by no one at the moment it happened, and by everyone in the days that followed. That is why this one use is real when the others were mirages, and that is why the governments of the world care about this technology, in a way they never cared about faster chemistry simulations. Because whoever builds that machine first, in secret, would hold a key to a very large fraction of the world's private information, at least until the world could change its locks. It is not a consumer product. It is not something that would make your morning easier or cure your illness. It is closer to a strategic weapon, a one-time skeleton key for the encrypted world, and the mere possibility of it is enough to reorder the priorities of nations. But now, having felt the weight of it, we have to be honest and careful, because the reality of this one real use is stranger, and in some ways smaller, than the nightmare makes it sound. The machine that could do this does not exist. It is not almost here in any meaningful sense, and even if it were, the key it holds is a much odder key than it first appears, a key that, the moment it is used, begins to destroy the very thing that gives it value. To see why, we have to look at just how far off that machine really is, and at what the world has quietly been doing to prepare for it, and when we do, the great terrifying threat is going to reveal a quiet anticlimax hiding inside it. Part 9. The Threat That Arrives. almost. The one genuine, undisputed use of a large quantum computer is to break the world's encryption, and yet that use is stranger than the fear around it lets on, because it arrives, like everything else in this story, only almost, and because the moment it finally arrives, it begins to erase its own reason for existing. Let us start with how far off it really is, because the distance matters, and it is almost always left out of the frightening version. Remember the canyon. To run Shor's method against the actual encryption that guards the actual internet, you do not need the hundreds of noisy qubits we have today. You need an error-corrected machine of enormous size. The estimates have moved around as the methods have improved, and I will give you the honest range rather than a single scary number. Not long ago, a careful estimate suggested that breaking one common size of encryption key would take something like 20 million of today's noisy physical qubits, running for hours. More recently, cleverer methods have brought that estimate down, and a revised figure suggested it might be done with under 1 million physical qubits. But look at both ends of that range, 20 million at the high end, under 1 million at the low end, and then look again at where we are, in the hundreds of qubits, maybe a bit past 1,000. Even the most optimistic version of the code-breaking machine is on the far side of the same immense canyon we have been standing at the edge of all night. It is not almost here. It is a decade away at the very least by most honest reckonings, and possibly much more, and possibly, if the canyon proves too hard to cross, never in the form we imagine. Consider how unusual this situation really is when you set it beside almost any other danger the world has ever faced. Most threats arrive first and are understood afterward, and the scramble to defend against them begins only once the damage has started. A new weapon appears, and then armor is invented to stop it. A new disease spreads, and then the medicine is found. But here the order is reversed. The weapon has been described in complete detail for decades, its exact method known, its precise target named, and yet the weapon itself still does not exist and may not for many years. And into that strange gap, that long warning, the world has poured its preparation. The defenders have had a generation to work, and they have used it. They have built the new locks, tested them, argued over them, standardized them, and begun installing them across the systems that matter most, all before the burglar has taken his first step. It is as if a town had been told, with total certainty, that a particular thief would arrive sometime in the next 20 years and would pick exactly one kind of lock, and the town had calmly spent those years replacing every one of those locks, so that the thief, whenever he finally shows up, will find most of the doors already changed. That does not make the danger nothing. Some doors will not be changed in time, especially the doors of large, slow institutions with mountains of old systems, and there is always the quiet threat of the harvested archives, the sealed data being stored today against the hope of a key tomorrow. But it does mean that the great cinematic nightmare, the single machine switching on and laying the whole world bare in an afternoon, is being diffused deliberately and in advance, by people most of us will never hear about, working patiently on the unglamorous problem of changing the locks before the storm. There is a strange and quiet steadiness in that work, the steadiness of preparing calmly for a danger that has not yet arrived, and may arrive only almost, and it is the exact opposite of the panic the subject usually inspires. The people who understand this threat best are not panicking. They are methodically, lock by lock, making sure that when the almost finally becomes a now, if it ever does, it will open far less than it might have. So the first strange thing about the one real threat is that it too lives inside the word almost. Even the danger is perpetually just over the horizon. But there is a second strange thing, and it is stranger than the first, and almost nobody outside the field talks about it. The world is not waiting helplessly for the code-breaking machine to arrive. The world is already, right now, quietly changing its locks. Because here is the thing about that mathematical wall, the impossibility of factoring. It is not the only kind of wall we know how to build. Mathematicians and cryptographers, seeing Shor's result decades ago, understood the danger long before any machine could realize it, and they went to work designing new kinds of locks, new mathematical problems, chosen specifically because they are hard even for a quantum computer. Shor's method is a specialist. It is fearsomely good at factoring and a few closely related problems, and useless against most others. So the task was to build the world's new locks out of the problems Shor cannot pick, and that work has been done. In the year 2024, after years of careful international effort, the first official standards for this new kind of quantum-resistant encryption were finalized and published, ready to be rolled out across the systems of the world, The replacement locks exist. They are being installed. And they are being installed before the burglar they are meant to stop has even been built. Think about how odd that is. We are living through a very slow-motion, very strange kind of heist in which the thief has announced, decades in advance, exactly which lock he intends to pick, and the whole world has calmly begun replacing that lock with a different one he cannot pick, and the thief himself still does not exist, and may not exist for another decade or more. By the time the code-breaking quantum computer finally switches on, if it ever does, it may find that most of the doors worth opening have already been fitted with locks it cannot touch. And this reveals the quiet anticlimax hiding inside the one real threat. Even in the best case for the codebreakers, this is a one-time capability with a closing window. It is not a renewable product. Once the old locks are broken, and they get replaced, and then that is that. There is no repeat business in breaking a lock that everyone already knows is going to break and is busy replacing. The great terrifying use of the quantum computer turns out to be a single, enormous, historic event that the world is actively working to make anticlimactic before it ever happens. It is a doomsday that people are calmly diffusing in advance. There is one shadow that does remain, and honesty requires that I name it, because it is the one part of the threat that is real right now, tonight, before any machine exists. It is a strategy with a plain and chilling name. Harvest now, decrypt later. The idea is simple and patient and a little cold. If you believe that a code-breaking machine might exist 10 or 15 years from now, then there is something you can do today. You can collect encrypted information now, information you cannot yet read, and simply store it. Save the sealed letters, warehouse the locked data, wait. And if, someday, your machine finally crosses the canyon, you reach back into your archive and open everything you saved, all those years of secrets, all at once. So the one genuine, present-tense danger is not that your secrets can be read today. It is that a secret you send today, if it must stay secret for 15 or 20 years, might be sitting in someone's archive right now, waiting for a key that has not yet been cut. And that is a real reason for the world to be changing its locks with some urgency, even though the burglar is still only almost real. I want to let the human weight of this settle before we go on, because it is one of the true emotional centers of tonight, and it deserves stillness. Somewhere in the future there may be a day, a single ordinary morning, when the locks stop working. And on that morning, everything that was ever sealed and saved becomes readable. Not just the state secrets and the bank records, but the small and human things too. The private messages, the words people wrote believing no one else would ever see them, the ordinary griefs and confessions and tendernesses that everyone entrusted to the sealed and silent care of that mathematical wall. All of it, potentially open. And then, in the same breath, the strange and almost gentle anticlimax. Because we saw it coming. Because we are already, calmly, quietly, changing the locks, years ahead of the morning, so that when it finally arrives, if it ever does, it may open mostly empty rooms. There is something almost tender in that, in a civilization that looks a distant danger in the eye and without panic simply starts getting ready, replacing the locks one by one while the rest of us sleep, so that the great unlocking, when it comes, finds far less to unlock than it might have. The threat is real, and the response is already underway, and both of those things arrive as everything in this story arrives, only almost, and never quite on the day we were told. So if the one real use is this strange, distant, self-erasing thing, a doomsday the world is diffusing before it goes off, then we are left with the single hardest question of the entire night. The question that should have been nagging at you for the last hour. If the everyday uses have emptied out, and the one real use is a decade away and busy being made anticlimactic, then why, right now, is more money than ever before in history being poured into this technology? That is the genuinely strange thing, and the answer is not what you would guess. Part 10. Why the world is betting anyway. If a technology's users were quietly emptying out, you would expect the money to follow them out the door, and instead the opposite is happening, and that reversal is the single strangest fact in this entire story. Let me lay the numbers in front of you, because they are genuinely astonishing, and they are recent. In the spring of the year 2026, the government of the United States announced that it would put around $2 billion into quantum computing, spread across 9 companies, and it would do so in an unusual way, not simply as grants, but by taking ownership stakes in the businesses themselves, becoming in effect a part owner of the industry it was funding. The largest single share, roughly $1 billion, was directed toward one major company. Another large chip manufacturing firm was set to receive something like $375 million. Several other quantum companies, some of them small, some barely more than promising laboratories, stood to receive around $100 million each. $2 billion of public money poured into a technology that, as of that very moment, had no proven practical use. Read that sentence twice, because it is the truth we have spent all night earning. $2 billion into a technology whose everyday applications keep dissolving and whose one real use is a decade away and busy being made anticlimactic. And it was not only one country. Across the world, another great power had already made the same bet, and larger. In its newest long-term national plan, approved earlier that same year, quantum technology was placed at the very top of a list of future industries, named first, ahead of everything else, as an engine of national growth and backed by a scale of funding that ran into the tens of billions, with something on the order of $17.5 billion channeled through regional funds toward building not just the science, but the whole commercial industry around it. Two of the most powerful governments on Earth, spending sums that could fund entire scientific fields many times over, on a machine that cannot yet do the thing it was promised to do. There is something worth pausing on in the shape of that first investment in particular, because it is unusual enough to tell you how seriously this is being taken. Governments fund research all the time. That is ordinary. But taking direct ownership stakes in the companies, becoming a shareholder rather than merely a patron, is a different and heavier kind of commitment. It is the posture of a state that does not want to simply encourage an industry from a polite distance, but to bind its own fate to that industry's success, to sit inside it, to hold a piece of whatever it becomes. You do that for things you consider strategic, things closer to steel and energy and weapons than to ordinary commerce. And the spread of the money tells the same story. It went not to a single favoured champion, but across 9 different companies at once, some of them large and established, some of them small and unproven, as if the government were not backing a winner it had already identified but buying tickets in every lane at once, unwilling to bet on which approach will cross the canyon, and unwilling, even more, to have no ticket in the lane that does. That is not how you spend when you know what you're doing. It is how you spend when you're afraid of not being in the room, and it quietly reframes every optimistic announcement about foundries and leadership and ecosystems. Underneath the confident language of building the future, the actual behaviour, the ownership stakes, the spreading of bets across every approach, the sheer size of the sums set against the absence of any proven return, is the behaviour of institutions hedging against a fear they cannot quite say out loud. Not, we know this will pay, but rather, we cannot be the ones who sat it out and were wrong. And listen to the language that came with the money, because the language tells you what people want to believe. There was talk of building a quantum foundry, a factory for quantum chips, of manufacturing quantum wafers to secure a nation's quantum leadership, its quantum innovation, its quantum ecosystem. The word quantum was applied to everything, over and over, until it stopped meaning very much at all and started functioning as a kind of incantation, a word you say to make a thing sound like the future. And underneath the incantation was a very old and very ordinary idea about how technology progresses. The idea was that the hard part is manufacturing. Build the factories, print the wafers, make enough of the chips, and the revolution will follow, the way it followed for ordinary computer chips, which got cheaper and more plentiful year after year until they remade the world. But we have spent all night learning why that idea is misplaced here, and now the phrase I planted earlier comes back to do its work. The hard part was never the chip. We can already build the chips. We can print the qubits onto their special wafers, using adapted versions of the same techniques that make ordinary computer chips, though the wiring has to be made of exotic materials that only become superconducting in extreme cold. Manufacturing the hardware is difficult, yes, but it is a difficulty we largely know how to handle. It was never the true obstacle. The true obstacle, the one no foundry can solve, is finding something useful for the finished machine to do, and making enough qubits work together reliably enough to do it. You cannot manufacture your way across the canyon. You cannot print a use case onto a wafer. And so there is something almost poignant about all those billions flowing toward foundries and factories, towards solving the part of the problem that was never really the problem, while the actual mystery, what are these machines for, and can they be made to work at the scale that matters, remains exactly as open as it was before the money arrived. So why do it? Why would serious governments, advised by serious people, pour fortunes into the one part of the problem that is not the bottleneck, for a technology whose uses keep evaporating? And here, at last, is the answer, and it is not stupidity, and it is not simply waste, though it may partly be both. The answer is fear, and the particular shape of the fear makes the whole strange bet suddenly rational. Remember the one real use, the code breaking, the skeleton key for the encrypted world. Now imagine you are a government, and you ask yourself a single question. What happens if someone else builds that machine first, and we do not have one? The answer is unbearable. If a rival power crossed the canyon in secret and held the key to the world's encryption, while you had nothing, the disadvantage would be catastrophic and possibly irreversible. And so the calculation is not, will this pay off next year? The calculation is, can we afford to be the ones who are wrong, the ones who guessed it would never work and then watch someone else make it work? And the answer to that question, for a nation, is no. You cannot afford it. The downside of being wrong is too large. This is what the billions actually are. They are not a forecast. They are insurance. They are a hedge against a future that is unlikely but so dangerous that its mere possibility is worth almost any premium. It is a wager placed not because the prize is probable, but because the cost of not holding a ticket should the improbable prize be drawn is annihilating. And that reframing, once you see it, is oddly clarifying, because it explains a puzzle that would otherwise make no sense at all. Set two great scientific dreams side by side. On one side, the effort to build a small star on Earth and draw clean and almost limitless energy from it, a dream whose payoff, if it came, would be light and warmth and power for every person alive, a gift so plainly good that no one would need it explained. On the other side, a machine whose one certain use is to break the locks that guard the world's secrets. Now ask which of the two receives more money right now from the most powerful governments on Earth. It is not the star, it is the lock breaker. The dream of shared and gentle abundance draws only a fraction of what flows toward the machine of secrets. And that ordering, that strange and slightly sorrowful ordering, tells you something true about how the world actually decides where its treasure goes. It is not moved most powerfully by the size of a possible good. It is moved most powerfully by the size of a possible loss, by the fear of a rival's advantage, by the unbearable thought of being the one who was wrong while someone else was right. Hope opens hands slowly. Fear opens them at once. And the budget of our moment, poured toward the cold machine of secrets rather than the warm machine of light, is written in the handwriting of fear. And once you see it that way, the strange reversal resolves. The money grows as the near-term uses shrink, because the money was never really about the near-term uses. It was always, underneath, about that one distant, dangerous, decade-away key, and about the unthinkable cost of letting someone else hold it alone. There is one comparison that makes the strangeness of all this land with full force, and I will leave it with you as we move toward the quieter waters of tonight. Consider another great scientific dream, nuclear fusion, the effort to build a star on Earth and draw clean, almost limitless energy from it. Fusion has a clearer path to a payoff that everyone can understand and everyone would want. Power for the whole world, and yet fusion receives only a fraction of the funding now flooding toward quantum computing. Think about what that says about us. We are pouring more into the machine whose great use is breaking secrets than into the machine whose great use is lighting cities, not because breaking secrets is more valuable than light, but because the fear of a rival's secret weapon moves us more powerfully than the hope of a shared and gentle good. The budget is being written by dread rather than by benefit, and there is something worth sitting with in that, quietly, in the way we sit with things here. Picture the whole of it from a distance now. Picture nations, the most powerful organizations that human beings have ever built, gathered around a machine that does not yet work, cannot yet do the one thing they most fear it will someday do, and cannot yet do the everyday things it was sold on at all. And picture them, one after another, laying down fortunes on the table anyway, staking sums that could reshape whole fields of science, not because anyone can show them the machine will pay, but because none of them can bear to be the one who walked away and was wrong. It is a strange and human and almost sorrowful thing to watch, a civilization wagering its treasure not on a promise it believes, but on a fear it cannot shake. And it raises finally the question we have been walking toward all night, gently, from the very first minute. If this is where we have ended up betting fortunes on a maybe, then what exactly does it mean to say the thing I promised at the very beginning we would earn? What does it actually mean to admit that we were wrong? Part 11. What it means to be wrong. We were wrong. I said at the start of tonight that I wanted to earn that phrase gently, rather than throw it like an accusation, and now, having walked all this way together, I think we finally can hold it in our hands and turn it over and see what it truly is. Because being wrong, in the way we were wrong about this, is not the shameful thing it sounds like. It is something quieter and more honest, and in the end almost consoling. Let me gather up exactly what we were wrong about, because vagueness helps no one, and the specifics turn out to be strangely gentle. We were wrong about the timeline. That is the first and largest of it. We were told in 1,000 ways that the quantum computer was almost here, and we believed that almost, and the almost was never true in the way we heard it. The useful machine was never a year or two away. It was always on the far side of an immense canyon, and the word almost was doing quiet, heroic work to make that canyon feel like a doorstep. We were wrong about the breadth too. We imagined a universal machine, better at everything, and it was never that. It was always a strange and narrow instrument, spectacular for a tiny handful of problems and unremarkable for nearly everything else, a key cut for a few unusual locks. And we were partly wrong, most subtly of all, about the purpose. We thought its purpose was to transform medicine and materials and money and mind, and instead its one certain purpose turned out to be a single, dangerous, self-erasing act of code-breaking, wrapped around a long, patient, uncertain scientific frontier that may or may not ever open into the everyday world. That is a great deal to have been wrong about. And here is the turn, the thing I have been carrying carefully all night to give you now, at the moment it can land with its full weight. Being wrong about the hype is not the same as the science being false. This is the most important sentence I will say tonight, so let me say it slowly. The fact that we were wrong about when and how broadly, and for what, does not mean that any of it was fake. It was not a scam. It was not vaporware. It was not a decade of people knowingly selling nothing. The machines are real. The beautiful trick, the entangled cord of possibilities, the sculpting of waves so the wrong answers cancel and the right one rings out, all of that is real, and it works, and it is one of the most remarkable things the human mind has ever built. The disappointment we have traced all night is not the disappointment of discovering a fraud. It is the gentler, more ordinary disappointment of discovering that a real and hard and beautiful thing is further away and narrower and stranger than the excitement around it ever admitted. And there is real progress, genuine progress, that deserves to be honoured even as we let go of the hype. Even as I tell you the useful machine is far off, I have to tell you also that the people chasing it have been achieving things that, a few years ago, were not certain to be achievable at all. The single hardest problem, the one that has haunted this field from the beginning, is the fragility of the qubit, the way its quantum state leaks away into the world at the faintest disturbance. And recently the effort to fix that, the effort to build error correction that actually works, crossed a threshold that matters. A leading laboratory showed, not in theory but in a real machine, that as they made their error-correcting scheme larger, the errors got smaller rather than piling up. That may sound modest, but it is not modest at all. For years it was an open question whether error correction would even work in practice, whether adding more qubits to protect a calculation would help faster than the added qubits themselves introduced new mistakes. And the answer, demonstrated in real hardware, turned out to be yes, it can work. The errors can be made to shrink as the machine grows. That is a real brick laid on the far side of the canyon. It does not mean the machine is almost here, but it means the bridge is being built by people who know exactly how wide the canyon is and are laying stone anyway, honestly, one piece at a time. I want to take you, before we leave the machines behind, into the one place tonight that shows you both truths at once, the reality and the difficulty, the wonder and the distance, all in a single image. I want to take you inside the machine itself, into the cold at its center. Imagine descending into one of these quantum computers, layer by layer. From the outside, it does not look like the sleek silver chip of the imagination. It looks like a strange golden chandelier hanging upside down, a tiered cascade of gleaming plates and coiled tubes, each level colder than the one above it. You pass the first stage, already colder than a winter night. You pass the next, colder than the surface of any planet in our solar system. You keep descending, through stage after stage of shielding and cooling, and the cold becomes something almost unimaginable, until at the very bottom, on the smallest plate at the centre of it all, you reach a temperature of around 15 thousandths of a single degree above absolute zero, the lowest temperature there is. That is colder than the empty space between the stars, which still glows faintly with the warmth left over from the birth of the universe, around 2.5 degrees above absolute zero. This machine is hundreds of times colder than interstellar space itself. Humans have built in a laboratory one of the coldest places in the known universe, and they have done it on purpose, for one reason. Because only in that profound and total stillness, only when almost every last tremor of heat has been stripped away, can a single qubit hold its fragile cord of possibility steady for even a breath before the warmth of the world reaches in and collapses it. That is what one flicker of quantum computation costs. A cathedral of cold, hundreds of times emptier of heat than the space between stars, built to protect a whisper that lasts a fraction of a second. When you feel how much care, how much cold, how much sheer human stubbornness goes into holding that whisper steady, you stop asking why the useful machine is not here yet, and you start marvelling that the whisper can be held at all. Hold that image against everything the marketing ever told you, and feel how different the two pictures are. The marketing showed you a finished machine, humming confidently, about to remake the world any day now. The truth is a golden chandelier of cold, hundreds of times emptier of heat than the space between the stars, straining with everything it has to keep a single fragile whisper alive for a fraction of a second. Both pictures are of the same technology, but one is a promise dressed up as an arrival, and the other is an honest portrait of a frontier, and the honest portrait is, to me, far more moving than the promise ever was. There is more genuine wonder in the true difficulty than there ever was in the false ease. It is harder to sell a whisper held in the cold than a revolution arriving on schedule. But it is real, and the revolution on schedule never was. And this is why being wrong and being deceived are not the same thing, and why it matters so much to keep them apart tonight. If this were a fraud, the right response would be anger, and the right conclusion would be to walk away and trust none of it. But it is not a fraud. It is a real and beautiful and monstrously hard thing that a great many honest people are working on, wrapped in a layer of hope and hype and fear that ran far ahead of the work. The error was not in the laboratory. The error was in the story told about the laboratory, the story that turned a canyon into a doorstep and a whisper into a certainty. And the correction is not to stop believing in the machines. The correction is to stop believing the story and to look instead at the machines themselves, cold and fragile and real, and to hold them to the far gentler and far more honest standard of what they can actually, presently do. Which is little for now, and which is for now a kind of magnificent, difficult beginning rather than an arrival. The hard part was never the chip. Now, at last, that phrase can mean what it was always going to mean. The hard part is the cold, and the fragility, and the finding of a use worth all this care. The hard part is the part that is still unfinished, and that is not a scandal. That is simply what a real frontier looks like when you finally strip away the hype and see it plainly. It is difficult, and it is beautiful, and it is honest, and it is not almost here. And there is a strange peace in finally being able to say all four of those things at once, without pretending, without selling, without fear. Which is, I think, exactly where we should stand as we let tonight come to its close. Part 12. The Honest Horizon. The quantum computer may still arrive. I want to be clear about that as we drift toward the end, because it would be just as much a mistake to swing from blind hope into blind dismissal, and dismissal is only the hype turned inside out. The bricks are being laid on the far side of the canyon by people who know how wide it is. The whisper can be held in the cold. Someday, perhaps, the useful machine may cross over, and if it does, some of the promises we have watched dissolve tonight may quietly reform into something real. I do not know whether that day is 10 years off or a generation off, or whether the particular path we are on will ever quite reach it. Nobody knows. And the honest thing, the thing this whole long walk has been leading toward, is simply to be able to say that we do not know, and to say it without either the salesman's certainty or the cynic's sneer. Because look at what the last few years have actually taught us. Underneath all the roadmaps and the billions and the vanishing numbers, they have taught us the distance between a promise and a machine. They have taught us how easily a canyon can be dressed up as a doorstep, how gracefully a goalpost can be moved when no one wants to announce that it moved, how a single warm word like almost can carry a great deal of hope across a gap it was never strong enough to bridge. And they have taught us something about ourselves too, something worth carrying far beyond this one technology. They have shown us a whole civilization deciding to spend its treasure chasing a thing it cannot yet use and cannot afford to be wrong about, moved more by the fear of a rival's secret than by the hope of a shared good. That is not a fact about quantum computers. That is a fact about us, revealed by quantum computers, and it will be just as true about the next great promised machine, and the one after that. So what do we do with the phrase we finally earned? The phrase on the thumbnail, the two small words we have been turning over all night. We were wrong. I said it would not be an embarrassment by the time we got here, and I hope you feel now why. Being wrong is not the opposite of doing science. Being wrong is how science moves. Every honest map of an unknown country is drawn, erased, and drawn again, and the erasing is not a failure of the mapmaker, but the very act of learning where the rivers actually run. We drew a map of the quantum future with the coastlines too close, and the harbours too many, and now, slowly, we are erasing it and drawing a truer one, with the canyon marked in its real width, and the one strange harbour of code-breaking set honestly at its far and distant edge, and a great deal of open, uncharted interior left blank, marked only with the most honest words any map can carry. We do not know yet. There is a quiet dignity in being able to write those words on the map and mean them, rather than filling the emptiness with confident inventions. That dignity is what was missing from the roadmaps, and it is what we can choose to carry forward instead. I think, too, that there is a small comfort in all of this, if you let yourself find it, and it is a comfort worth carrying towards sleep. We live in a time that is very good at telling us the future has already been decided, that the machines are coming, that the only question is how fast, that resistance or even doubt is a kind of foolishness. And the honest story of quantum computing quietly refuses all of that. It shows a future that has not been decided at all, that is still genuinely open, still being argued over in the cold rooms of laboratories by people who do not yet know how it ends. The canyon has not been crossed, the uses have not been found, the machine that changes everything has not been built, and may not be, at least not soon, at least not the way we were told. And rather than finding that frightening, I find it strangely freeing. It means the future is not a finished thing rushing toward us on rails. It means the future is still being written, slowly, honestly, one corrected map at a time, by people willing to say the two hardest and most hopeful words in all of science. We do not know, because not knowing, held honestly, is not the end of the story. It is the exact place where all real discovery has always begun. Here is the thought I want to leave you with, as the cold machines hum on in their laboratories and the billions move and the locks are quietly changed all over the world. We keep treating the future as a countdown, as a set of dates we are marching toward, a morning when the news will break and everything will change at once. And the whole story of tonight is the story of that countdown failing, again and again, the clock resetting each time we looked away. But maybe the countdown was always the wrong picture. Maybe the future is not a countdown at all. Maybe it is not a date we are approaching, but a question we're still learning how to ask, and the asking is slow and honest and unfinished, and the answer arrives not on a schedule but in the patient, uncertain way that all real understanding arrives, a little at a time, in the cold, held steady for a breath, and then a breath longer. We were told it was almost here, and almost, it turns out, was never a measure of time at all. It was a measure of how much we wanted it, and of how far we still had to go, and of how gently the truth waits for us to be ready to admit that we were wrong, so that we can begin, at last, to be right. Rest easy. The machines will keep their cold vigil through the night, holding their fragile whisper against the dark, and the honest horizon, wherever it truly lies, will still be there in the morning, waiting to be mapped a little more truly than before.